like 60, 70 people already. So I'll give it over to Aldo to start the presentation today. Very quickly, Aldo Pareja has been there in the team since the very beginning when the team didn't exist. Uh, Aldo has led the training pipeline in Instruct Lab. So whatever you see in Instruct Lab came from some happy accidents, some very late night work, some long stretches of things, which he will talk about. And very recently, we put all that knowledge into a paper that luckily got accepted at iClear, which is, again, one of our top conferences in machine learning with a very, very low acceptance rate. And this paper essentially describes how Instruct Lab works once you have a data set. How do you take that data set and what do you do to put that data set into the model? You must have heard about multi-phase training, phases, and all that PyTorch stuff. How that came to be is basically the story that this paper tells. But why is it a paper? Well, and Aldo will actually shed a lot of light on it. Instruction tuning, or especially full fine tuning, where you change all the weights, is an incredibly complicated problem. It is so complicated that before this paper, nobody has actually attempted to write a systematic scientific report or scientific account of how do you go and make it happen. And the reason it's complicated primarily is because there's a lot of levers you can pull. There's a lot of hyperparameters, a lot of things to choose. How do you make those decisions? And I don't know if you've ever wondered, like, how exactly it is that every single time you run Instruct Lab training, it works. It doesn't crash. It doesn't go into some digression on the gradient norm or loss blowing up. And so this paper. The primary reason it got accepted is because it's essentially said all this millions of levers that you have to hire expensive PhDs to figure out, can we convert that into a recipe that anybody can execute? And that conversion of the complexity into a recipe was driven by, I want to say, at least 200-300 experiments that went into this paper. Aldo will try to cover some of that. Those I would encourage that maybe let him initially give you an overview of what the what instruction tuning actually is. Get into the paper, and then we start asking questions. But obviously, if there's a burning question, disrupt anytime, and we'll take it. Okay, over to you, Aldo.
All right, thank you for the introduction, Akash. So as Akash was saying, there is a lot of complexity in instruction tuning. There are a lot of engineering levers and also scientific levers, and there's no actual kind of consensus of how to do this, and the consensuses that we were finding were not giving us the right results. And what I want to show you today is kind of like introducing all of that complexity behind instruction tuning. What is it, and how we in Instruct Lab kind of made it into a simple recipe and also training library that basically is pretty robust across different model families and sizes. And this is the story of how all of those experiments and how all of the engineering challenges and problems that we faced over several years have come up to like just a simple iLab train command, right? All right. So with that, with no further ado, let me start by telling you what is instruction tuning. So instruction tuning is a process where a language model is specifically trained to follow user instructions more accurately. So you can have like a prompt, so something like describe the weather today, right? And then in a pre-trained model, which is more of an auto-completion model, it would just auto-complete it. So it is sunny and warm today. Today the weather is sunny and warm, and it can get into repetition cycles and it never ends because it's just an auto-completion engine. What you want with instruction tuning is for the model to be useful and actually answer your question concisely and accurately. So instead of saying something like that, it would say something like the weather today is sunny with a high of 75 degrees and a light breeze, because that's what you want. It might not be the most likely token given a pre-trained model, but it is the thing that you want the model to answer. And instruction tuning is about getting a pre-trained model, a next token prediction model, and make it follow these kind of instructions. So how is it done? You need a pre-trained model where, let's say, most of the knowledge and most of the like the English and skills and things are like in a sea of data, and you just put all of that data into a model. You collect a data set of instructions or prompts, something like, for example, I don't know, mathematical problems are the way to solve them. That is a mathematical data set. And if you want your model to be good at math, that's probably how you would start. Then you fine tune the model on this data set, right? Which is what iLab Train does. And then you will do a bunch of other stuff. For example, the DeepSeek R1 paper, what they do is reinforcement learning with verifiable rewards. And that helps the model kind of like achieve these long chain reasoning processes that help them be much more accurate in high complex problems. And then preference tuning, which is something that you can do for alignment and also variance reduction over the different answers that a model can give you. And then you evaluate that performance. So you need also have the same way that you do test-driven development in machine learning, you do evaluation-driven development. So you evaluate on empty bench and all of the different benchmarks that really measure quantitatively how much progress you have done with respect to the previous iteration. And then you iterate. So basically you come back to the drawing board, you come up with different techniques, you invest a lot of time and effort in processing the data sets, and so on and so forth. And then instruction tuning then is going to be instruction tuning versus pre-training. So in pre-training, you just have a model that is very good at predicting the next token. And what is the most likely word to come after the current word, given like the English language as in general. But in instruction tuning, what we want to do is to learn to predict the answer given a question. So it's different. You're not predicting just the next most probable word, but you're predicting you're trying to predict the most probable answer given a whole question, not just a word or a sequence of words. So let's focus on fine tuning, which is what iLab Train is and also what the paper was about. There is a lot of complexity in fine tuning. You first need to format the data and tokenize it, and you have a prompt and an answer, and you can have multiple turns of them. You need to transform these things into tokens. You need to mask them, so attend only to tokens of the same sentence. So if you have several sentences in a single kind of line of tokens, you need to properly mask them to not attend to other sentences. You need to compute a loss on what would be just the model responses, but not the questions. And then there is a lot of optimizations for throughput and memory and distributed training, which is something that the library takes into account. So there's gradient accumulation, gradient clipping, a lot of hyperparameters, memory considerations, how do you shard the model, and also gradient checkpointing. There's a bunch of techniques that it would be a whole talk to just talk about one of them. But all of those things kind of like get solved for you in the library. And then there is efficient fine-tuning, which we're going to talk about at the end. But let's just talk about what would be instruction tuning. How do you maximize the probability of the answer given the question? Should be just simple, right? Like you just minimize the loss and that's it. But in reality, there's a lot of different components. So you need to properly do the tokenization, apply the chat template. You need to have the embedding lookup layer aligned with such tokens. You need to have a causal attention masking that is not attending to anything else but the things that you expected it to do. You need to do cross entropy only on the answers. You need to do a stochastic gradient descent and then also explore different optimizers like Adam with DK or other things. You need to set up the multi-node distributed training, do gradient checkpointing, do chart the model, the gradients, the optimizer states, and then do computational optimizations like kernel fusion via torch.compile. And then there's a lot of engineering complexity, but also scientific complexity, right? And then the scientific complexity is like, there's actually not a mathematical or conceptual framework that tells you how do you actually fine-tune these models to get to the right, or to robustly kind of embed a data set into the knowledge of a model, and into the weights of a model, right? And at the time when we were starting InstructLab, or even when it was not called InstructLab, we were just fine-tuning models, basically. We were trying to solve that question. And at the time, the thing that kind of came, or that was the most popular, was Tulu 2. Today it's called Tulu 3 by the Allen Institute of Artificial Intelligence. And then this is what they would recommend. Just do 2 epochs, no weight decay, there is a particular batch size, there's a precision, the maximum sequence length, and then the effective batch size. And then with that, they were like the Bible of fine-tuning. And we were actually following that or trying.
And I just want to make a statement here. Like I like the fact that Aldo called it the Bible of fine-tuning, because none of this was actually based in any actual science. They did something that worked one time and they put it out there, and people just believe that yes, it is the right way to do this thing. And
nobody did any scientific study of it. Like nobody tried any ablations. Like, what if we change the batch size or the epochs or whatever? Like there was literally nothing about it on fine-tuning foundation models. There was a lot of information on like how to do this in general in like from scratch neural networks that were not even transformers. But nobody has done it for fine-tuning large language models, and that was the question that we had. But we found out that it's not just Tulu, right? And let me tell you a very cool story of how we kind of realized that Tulu was not completely correct. So at 3 a.m. in the morning, like 2 years ago or something, I was trying to train something with the Tulu hyperparameters, and it completely crashed. But we had a deadline by like 9 a.m. So I needed to basically scale up training and use more GPUs in order to train the model faster. And by doing that, what I wanted to do was to scale the Tulu hyperparameters in like the theoretical right way. So you multiply everything by 10, and then there's a bunch of computations that you need to do on the learning rate so that it kind of like the noise of the stochastic gradient descent keeps the same scale. And that's what I thought I did, but I ended up making a mistake because it was pretty late. So I left the warm-up very, very long. And the warm-up is basically how long the learning rate takes to go to the goal learning rate. Because it was very long, what I effectively did was I lowered the learning rate quite a lot while keeping the batch size much higher. So I did something completely different. I increased the batch size by 10x, and I decreased the learning rate by 10x, something like that. And by doing that, we found something that we, at the end, called the miracle model. because we literally couldn't replicate that, the model's performance. And we did a lot of experiments trying to do it
I
the
remember
right
it was
way.
27 experiments after which we found this. And the reason actually, I really like this story because the reason was what Aldo did by mistake was so ridiculous in light of what was out there, Tulu and all that, that you would never actually try it. So when all options were exhausted, we were like, okay, you know what? Maybe we did the stupid thing. Let's try it again.
And that's how we actually managed to replicate the performance that we got on that model. And by doing that, we started kind of questioning much more, okay, maybe all of these fine-tuning best practices are not actually best practices. And that's how we got into this endeavor of building out this paper and this library, right? So all of that as kind of conversion to what today is InstructLab training or iLab training. But today I want to talk about not the scientific, not the engineering challenges that we have solved in InstructLab, but the scientific kind of like endeavor that we took, and is also part of the recipes that we use in InstructLab. And this is a paper that we wrote with the team. And I want to take this time to just thank everybody. And it's been like an amazing experience to just share and work with them. I learn every day, and my co-authors are extremely smart, extremely hardworking, and it's just great to be part of this team. So yeah, thank you to Nikhil in particular, and Hao and Krishna, but everybody in general, Akash, of course, for helping me kind of like develop this paper. But okay, so this paper is about like demystifying all of these best practices, or actually questioning what the best practices were at the moment, and trying to find what is like the best recipe to actually get a robust training like a robust training schema that would give you the best possible solution or the best possible performance, and regardless of what model or data set you're trying to train with. And let me start with the results. So to the question, how can we effectively fine-tune a small size large language model and instruction tuning datasets that cover a diverse set of knowledge and skills like we have in InstructLab? What we end up kind of saying in the paper is, look, if you just want to train, the best thing that you can do is just use a constant learning rate and put a very small warm-up ratio. You don't really need that much. Increase the batch size quite a lot and lower the learning rate compared to other experiments, compared to other frameworks. And then when you do that, you are more or less gonna match many other kind of like novelties while keeping a very simple kind of pipeline to train. But the main results of the paper are these four. So the first one is that larger batch sizes combined with lower learning rates improve generalization and performance on downstream benchmarks like MT-Bench or MMLU, and then leaderboard and some other measures that we have measured.
Do you want to expand a little bit on this, because I feel this
I'm going to go over each of them. So this is just like a gist of what the results are, but I'm going to go over each of the results separately. So the larger batch sizes, important. Early stage training dynamics, when you see them, that tells you if you're gonna be better or not than another training run just by looking at the loss and the grad norm. You kind of meet basically the warm-up steps, which is something that was not at all kind of tested in the literature. And you can and you don't need to phase the trainings into different stages. And we showed that if you stack everything together, you almost always match the performance of the phased without, but being a lot more sample efficient and also simplifying the engineering because you don't need to process the data into stages. But let me go over this more in detail. So stack versus phased training. As you can see in this table, on the scores of stacked training are usually higher. Let me see if I can put a pointer. Laser pointer, yes. So the scores of stacked training is usually higher than phased training, but not by a lot. It's they're basically the same. But the biggest difference here is that the samples that you take to go to peak performance when you're doing stacked training are way lower, almost half. Or less than half the samples that you need. So the computational requirements of doing stack training is a lot more efficient. Then there is the batch size. So a larger batch size usually helps as well. So which means, like as you can see in this table, if you increase the batch size from 128, which is what Tulu would recommend, to 4K, you get a better performance and across more benchmarks than this, but in general, this is true. But interestingly enough, when you have a lower batch size, you get to the peak performance of that batch size faster because you do grading steps. You do more grading steps per epoch. And that basically trains the model faster, but doesn't reach as high performance as you do with larger batch sizes. So for example, with 128 samples, you reach peak performance at 2 million samples, whereas with 4K batch size, you reach performance like almost double the time that you need to reach that performance. So that is a trade-off that you need to take into account if you're using a single GPU or something that is very slow, maybe lowering the batch size would be good for you. And then the learning rate schedulers, which is the warm-up and then the decay. So there's a lot of literature that supports that having a warm-up and a decay is really helps in getting a higher performance. This mostly happens because if you're thinking about an optimization landscape, if you increase the learning rate, then you are exploring more, and then when you decay the learning rate, you go deeper into the valleys of a nonlinear optimization problem. But what we found is that if you don't do that. You just keep a constant learning rate and have a very small warm-up or no warm-up at all. Given that the learning rate is very low and the batch sizes are very high, I think that compensates for the theoretical framework that I just mentioned. But again, we have not tested this, but it's a hypothesis that we have, but we didn't write because we haven't tested that. So yeah, learning rate schedulers not really necessary, which simplifies the engineering and also the robustness of the method. You don't need to think about how many samples you have so that you actually indicate the learning rate properly or anything like that. And then the effect of the learning rate itself is the lower the learning rate, the better performance you get. And this is something that you see here across a bunch of different benchmarks. So in general, higher learning rates, where like when you have a higher batch size, the theory says that you should also increase the learning rate so that the noise of your gradient kind of keeps on the same scale. But actually what we found is that lower learning rates are better. And then this is what you see here. The lowest learning rate that we tested is the one that gave the best performance. And so those are kind of like the main findings of the paper. And there's just one more that I don't have in the slides, but I want to show real quick, which is the training dynamics. So if you see here, we did a lot of experiments, and I watched these logs for so long, I kind of memorized them, and then we started finding out that when you have a training run, if that training run is giving you a higher loss, but at the same time a lower grad norm, or the norm of the gradient, the magnitude of the gradients that you were getting were lower, that usually leads to higher performance at the end of the run. So as you can see here, for example, our best performing empty bench score is the blue and the yellow line. But if you see here, the blue line has a lower grad norm than everything else, and at the same time it has a higher loss. So it is, at the same time, it is the lowest learning rate. Everything else was kept the same, but this is robust across batch sizes and different hyperparameters. In the paper you can find more details. But basically, we didn't write this because this would take us into a whole other landscape of literature. But when you have a lower gradient in your norm, in a lower norm in your gradient and a higher loss, it means that the landscape of your loss is flatter. And a flatter landscape of your loss means that you generalize better. And this is more or less what we try to describe in this part of the paper.
So I think one thing I wanted to point out, I'm actually kind of glad that Aldo went into this particular point, because part of what we tried to highlight is it is very, very complicated to know and tune all the knobs of instruction tuning. To give you an idea, most of the fine-tuning libraries that you find on Azure or AWS or OpenAI, there's a reason why they always only provide you with something as simple as LoRa or the low-rank approximation. We know LoRa compared to InstructLab or full fine-tuning leads to suboptimal performance and everything. That's very well documented everywhere. But the reason to do that is because they don't want to get into this complexity. They haven't yet figured out how to let an end user do this kind of fine-tuning every time and succeed every single time. The only takeaway, honestly, from everything that Aldo spoke so far is that all this complexity is abstracted away in the way InstructLab training works. And we have done, I do want to say, like 500-600 experiments to make sure every single norm or every single hyperparameters are set on a basis of an actual empirical result. I think that's basically the main reason why we are so confident that yes, synthetic data generation is a huge huge value prop of Instruct Lab, but we don't say it very often. The way we allow full fine tuning within of that synthetic data in Instruct Lab is just as important. And if you actually talk with other data scientists and other consulting firms like BCG and X and etc., they actually the thing that blew their mind more than the SDG, of course they recognize the SDG, was really the fact that we are one of the only people to allow full fine tuning so robustly every single time. Okay.
And then with that, that kind of like finishes more or less the results that are in the paper. What I wanted to go over very quickly, but not necessarily, was around all of the other engineering challenges that we have to undertake in order to make the Instruct Lab library training kind of like, robust and smooth for the experience of the user. But before that, if there are any questions, I'd be happy to take them now before we go into that. I think there were some in the chat. Let me see.
Yeah, check the chat.
See if I find them. I don't know how to do this. Okay. What do we think of the effectiveness of reducing the data size during training? Certainly, there is a loss of fidelity reducing from 32-bit to 16.8 or 4. Okay, so here you're talking about both quantization, which is the quantization of the model, and yes, that is known to trade off performance for compute. And I guess you're trying to make the analogy of how is that related to data size. So we have done, and Krishna and Hao and others in the team have done like a good job at basically finding that we have empirically done and created a subset selection algorithm that allows you to cover your data set semantically as much as possible while reducing its size. And we have tested empirically that if you train on that subset, you basically get the same performance as if you train on the full subset. So that basically the answer to that is the reducing the data size does not harm on performance as much as quantization does.
I think that was.
When are we going to see a description of how skills are built with?
That's not related to this topic.
What is the roadmap for training? Are there any key areas?
Tushar has an answer.
Tushar, do you want to chip in?
No, I was going to ask a question actually, but I agree with, some of this question we can answer a little later. But this technique, Aldo, is this something which is kind of lowering the rate of learning and increasing batch size? Are we going to introduce it in the product, or you think it's already there?
It's already there. So
Okay.
Basically, what this paper is about. So iLab training is a particular recipe of those hyperparameters.
Yeah.
This is the story of how and why you should trust those hyperparameters. Why is that every time the model works?
Okay.
Yeah. And if you're talking to other, customers, and when they ask this question, it is to kind of empower people. You can give them this paper and let them have confidence that this is not just some thing that will need data scientists to run and figure these tuning parameters out. That said, I want to take your question as the opportunity to say, now there will be some probably data scientists on some teams that would say, hey, we would like you to give us the ability to tune these things, right? Which is this advanced profile thing that we were talking about yesterday, which I think we anyways do for other product, where there's a one-click do everything for me, and dash advanced, and then I would pass my parameters.
There's the case. Python is the case for that.
Yeah.
Especially with all that.
There's a question. There's a question that basically is asking what is the benefit of fine tuning versus doing something like RAG plus prompt engineering. And we have benchmarked our models against GPT-4 with RAG. And when you fine tune on the knowledge extracted from the document, from like inner source or private documents that your customer might be interested in, a very small model, like a 7 billion model, can overperform GPT-4 plus RAG on that particular knowledge with a much simpler engineering pipeline because it's literally just the model as a chatbot. Of course, you can still attach whatever RAG system your customer has to this model, and it still overperforms GPT-4. But it's a much simpler, much easier, cheaper version of what would be a RAG plus prompt engineering pipeline.
I mean, if there's interest in discussing this question, although it's not directly related to the talk today, the basic reason or the scientific reason why that is true is because when you are running a RAG pipeline, language model is just one component. The reason RAG performance is not up to the mark is actually majority of the time, if you actually check the literature, is because the retriever fails to retrieve the right chunks. Now, in a large meta study, it was found that retriever accuracy saturates around 75%. Now, how do you go and close that gap is the question that we tackle in InstructLab. When you have taken the same documents and trained the model with the documents, and now you are putting that in a RAG setup, every time the retriever fails, the model looks up its memory for the answer. That's where you see those spikes that we count. Let me go a step further, show you why we say this thing all the time. Here is a comparison where we ran a InstructLab aligned Granite, the previous generation Granite, that had the customer knowledge and was put in the same exact RAG setup as GPT-4, Llama 370B, Llama 3.1 405B, GPT-4o, and actually the last one, maybe we can disclose now, that's actually the deal that happened with AT&T. In all of these cases, it's the same exact fact. When you're relying on RAG, you're not using your language model alone. The language model is bottlenecked by what retriever gives it. If the answer from the retriever, if the chunks from the retriever did not contain the answer, your language model will not be able to answer. But when you have that document also available in language model's parameters or its memory, that's why you see these tiny peaks. In those 20% of the cases, it outcompetes these models. This is not to say that GPT-4 is suboptimal than Granite. There's no free lunch here, right? We're not claiming that InstructLab True Granite is better than GPT-4. But you're almost giving GPT-4 a bad deal because your RAG system is not perfect. No RAG system is perfect, right? And I hope that point is a little bit clear with this one. But I do want to keep the topic of the discussion on the training. So maybe we can get back to it.
Shar wanted to say something.
Yeah, I just want to. I mean, for those of you who are definitely attending Red Hat 1, and I don't know, Trevor, if you are, or David, you are, and I think you would be. There'll be multiple breakout sessions on this. I know this kind of came up at the What's New, What's Next also. What are the use cases, etc. So I think in any case, I think to Akash's point, I think those are good questions, but I think they will be addressed in the Red Hat 1. So I highly encourage you to attend those sessions. And if you cannot, then definitely reach out to me offline, and I can send you some information on how to position these.
Yeah, and what we will do is we'll try to see if we can run a series on InstructLab Science. So just like we're doing training, we can also have the people who invented the synthetic data generation from the team come and talk about that. And then people who actually did the initial POCs come and talk about how exactly we got those results in subsequent talks of this series. Just let us know. There's a channel called Random Samples on our Slack. If there are topics that would help, the audience here, very, very happy to build the next few talks on that.
All right, so as I said, like what I wanted to very briefly go over, because I want to give Akash time to talk about DeepSeek.
I mean, we spoke a little bit on this. I mean, only the question. I just need 5 minutes.
All right, all right, and then so there are a lot of engineering challenges that we have to deal with and that we put in the InstructLab library. The first of them is, and the most important probably, is how do you use multi-node, multi-GPU, well, in our case it's multi-GPU, but the InstructLab training library is something that we also use, or a version of it that we also use in multi-node training scenarios. And is how do you chart your data, and how do you chart your model, and what kind of precisions do you use, and how do you make these, how do you maximize the throughput or the amount of tokens per second that you can process in these particular settings. So there's a lot of different concepts. There is tensor parallelism, pipeline parallelism, data parallelism. There is floating precision and other things that I will go over briefly. So the first thing is, how do you do data and model parallelism? This is a diagram that helps me explain this very, very well. So on the top row, you're gonna see how the model weights can be split over different GPUs. Imagine that you have 16 different GPUs. When you're doing data parallelism, your model weights are basically copied over each GPU. When you're doing model parallelism, you put your model weights get copied, get sharded across each GPU. So all of the weights of your model are gonna be separate. And then you do both. So maybe you shard your model across only 4 GPUs, and then your data across the whole cluster. And then, well, if you have a mixture of experts on this kind of stuff, you can also shard per expert and not the whole model. And then the data is kind of like the complement to that. When you're doing data parallelism, your data gets sharded across all GPUs. And then when you're doing model parallelism, your data gets copied across all GPUs. So you put the same data on all the GPUs, but you give the same data to different parts of the model, and then you concatenate all of that to actually compute the training signals. So that is more or less the different things that you can do with model and data parallelism. In InstructLab in particular, we simply use FSDP Deep Stage 2, which is you shard the state optimizer, the optimizer state, but you copy the model weights, and then you do data parallelism. So your data gets charted across all GPUs, and different GPUs get different data points, and that increases the throughput as much as we that increases the throughput as close as optimal as you get, without getting into maintenance problems, because we have optimizations that are hard to maintain over time. And we basically outsource that to the PyTorch team, which is doing a great work with FSDP. So yeah, this was to explain what is DeepSpeed and FSDP, which is how to do model parallelism. But I went over that already. Floating point precision. So before the Ampere and Hopper architecture, people could not use BF16, which is a different way of expressing a float. So the difference between FP32 and FP16 is that your exponent has way less resolution, so your range is very low. And because the range because your range is very low, you end up kind of overflowing the model during the training process, and that has very nasty consequences. So what you do is that you decrease the precision of the mantissa, but you increase the precision of the information that you put in the exponent, and that way you can cover a bigger range at a lower precision, and that has been shown to be much more efficient when you're training. And then there's parameter efficient low fine tuning, which is something that the library also supports. This thing, you probably have seen it many times, but you have your pre-trained weights, you freeze them, and then you have a low ranking matrix adaptation that you actually train, and that reduces the number of parameters that you're training from like billions to like, I don't know, 100x less. And that makes your training way faster and much more efficient.
Yeah, but I think like this one, I also want to cover a little bit because this is a question that I think the field folks, definitely the sales team, the people who are engaged in POC often get, which is like, can I do LoRa instead of full fine tuning of InstructLab? The answer is no, because exactly of the reason what Aldo said, right? So what LoRa is saying is, hey, training all the parameters is very expensive. So I'm gonna create like 2 vectors per matrix and train those, and then just add to your original weight. There's 2 issues with this. When we are trying to introduce knowledge into your model, how much knowledge you can insert in a model is a function of how many parameters you can train. So think of these parameters in your model as some kind of a storage device that store your customer-related facts. In LoRa, you're reducing the number of these storage bits. Hence, you can store much lower amount of knowledge. That's the main reason that why we don't recommend for doing this on an enterprise level workload. The second reason is when you do LoRa on a particular area, so let's say you did it on, I don't know, back office standard operating procedure manual. Now, let's say it was only 3 pages, so it was not too much to learn. So you managed to learn something. The way you actually apply it is by adding the small vectors that you train, literally like an addition to the original matrix. What it does is that it shifts the model in a weird way. It says, and most likely what you see is the model can do the new task that you trained it on, but forgets everything else in the past. Or does a very strange behavior on the things that were, that it knew previously. That's the reason why we also have a taxonomy and why we always train on a taxonomy. Because what we are telling the model is that, yes, you need to learn this new thing, but do not forget anything else. Everything in the taxonomy is important to me. So that's one of the reasons why we do a full fine-tuning in InstructLab with the entire taxonomy every time. I hope that helps at least the field folks to kind of answer that question as to why we don't do LoRa, or maybe when it is useful. Yeah.
And then on top of LoRa, which is, there's QLoRa. So QLoRa is the same as LoRa, but you also quantize your model. So you reduce the parameter count or the parameter kind of like memory requirements by representing the weights with less bits. But that also, of course, decreases performance, and it decreases like significantly. But it enables you then to train much larger models on much less compute. Also something that we cannot do at InstructLab because it damages the models quite a bit, and it's not something that we can do at enterprise level.
By the way, these are all active areas of research. There are ways in which you can quantize, which can preserve certain tasks. And there's also a lot of research going on in parameter efficient tuning. But essentially, the mental picture I want you to take away is that if you want everything to work perfectly, memorization of new data, not forgetting the old thing, you start with full fine-tuning the taxonomy. That's the InstructLab way. Any reduction from there, in terms of, let's say you want to do LoRa or QLoRa, will cost you something. It won't come for free. There is this, like, we in machine learning, we like repeat this phrase, there's no free lunch, at least every lecture. And that's the same principle here. If you take something away, you're gonna take a hit in performance.
I mean, we're researching how to do this, but right now, it's on development. And well, this is to get mixture of experts, but that's a different thing. And that's it.
So, awesome. That's very well timed.
Yeah, thank you so much for attending. If you guys wanna have if you guys want me to answer any questions, feel free to just unmute yourself and ask them away.
Go ahead, Rich.
Yeah, it was a question there going back to your comments about the Q-LoRa, and I understand what you're talking about with the LoRa, Q-LoRa, this performance efficient tuning in general. Are we looking at how InstructLab might support mixture of experts and how we could perhaps potentially get logically smaller models supporting different branches within the taxonomy?
So Rich, no, yeah. So the InstructLab right now is of course tailored for Granite.
Right.
Granite is a dense model; it's not a mixture of experts. But InstructLab is agnostic to the base model that you use. You can use any model that you want, and there are some mixture of experts out there that are pretty good. Also produced, there are some produced by IBM, especially on the lower end of parameters, and is not something that you should put in Rel AI, because for that we need to do a lot of testing to make sure that it's gonna work.
Yeah.
But in the open source version, you can put any model and it's gonna work. Like, it's not gonna give you an error.
Yeah, I think that's a great point. One other thing to also realize is that mixture of expert is already there in Rel AI. That's your teacher model. Your teacher model is a mixture of experts. So we've been supporting it since before InstructLab was a thing.
Yeah, and I'm just curiosity, just kind of poking at it a little bit. Would an output of our alignment potentially in the future be resulting in a mixture of experts?
So I mean, if you make your teacher model a mixture of experts, then it will, as Aldo said, will produce a mixture of experts.
Well, as students, you mentioned as students.
student model.
We're not starting with a dense model and then producing a mixture of experts. No, that's not what InstructLab does.
I don't think any method does.
Yeah, no post-training method currently does that reliably. Yeah. So it depends on what base model you start with.
Fair point, and thank you for what you've done already with what we're using with InstructLab. I'm just kind of curious about other things, that's all.
Oh, okay.
But I mean, to your point, Rich, technically we support it. Right. The technique is agnostic. You can apply it really to any model.
Thank you.
I think there's also one from Neil in the chat, which is is the team looking at the stuff coming out of Onslaught? Yeah. Neil, we've been looking. So actually, I'll say Onslaught is probably one of the only startups out there that also allows you to do a hands-off instruction tuning. The thing that they don't, so they are really in the business of like, whatever data is there, we'll take it. You can run the training. They don't work on the same principles of recipes for making sure you will successfully manage to insert your customer data in it. And what I mean is like you will beat the RAG plus GPT-4, and B, it's very much it's a prescriptive paradigm where it's not been optimized for the workload of custom skills, but definitely we're looking at it to see what they're adding.
So I've followed Onslaught since its beginning. Not all the time, so I don't know the latest updates, but I know they focus mostly on lower end hardware training. So they try to increase the throughput and the amount of and like also decrease the bar that you need from the hardware level to be able to train. As I remember, it does not allow for more than single node training, and also it is very focused on quantization plus like not LoRa, but like LoRa or parameter efficient methods that are like more state-of-the-art parameter efficient methods to do your training. But again, they are more focused on getting the thing to train on lower end hardware not as much on getting the best performance out of the models that they're training.
Yeah, I think that's a better. Josh, you had a
So first of all, again, thank you for this session. I love all of these calls. My question is around, like, when it comes to training or fine-tuning a model, is there a size limit on the data? And let me give some context here. So our Lightspeed product teams are trying to take Granite and either use a RAG setup or do InstructLab fine-tuning on things like OpenShift product documentation, RHEL product documentation, knowledge base articles for all of our products. And so, like, we have an open question among those teams. Should we do one model with all of that data in the InstructLab mix, or should we do multiple discrete models? Because, like, right now, the performance they're getting from anything they try isn't fantastic, and they don't know why.
I think those are two separate questions. So maybe the first one is, depending on how much data you have or how many products you're targeting, it's totally fair to put them all in one model. An 8B model can store a reasonable amount of information. If there's too much overlap between two product manuals, you might just want to separate them because it will add to the confusion or something like that. But from a data size point of view, there is a lot of space. So by some estimate, a 7B model parameter, a 7 billion parameter model, can store all of Wikipedia. So there's a lot of room in some sense. The second question is that they're not seeing good performance. I think that will probably have to tackle slightly else, because these the kind of documents you're mentioning, actually some of the numbers I showed you are on that. This is actually a category that has worked very well in most of the experiments. So it'd be interesting to find out why. If I were to take a guess, Josh, it will be on how it is being chunked and how it is, what are the Q&A or YAML. 90% of the time, it's a combination of the two. But I'm pretty positive that on product manual, they should get very good results, especially like beat the proprietary plus RAG setup.
Yeah, well, and like, to be clear, like, there is a level of experimentation they're still going through. So, like, they're doing RAG, they're doing tuning, they're doing Raft, right? So, like, they're trying everything and seeing what sticks. Okay. And then if they start throwing in K-base articles and solutions, that's a little bit of like that whole data quality, crap in, crap out kind of problem. Yeah. So it's really just like I'm trying to get a better understanding of, like, from a tuning perspective, like, okay, so if a 7 billion parameter model can store all of Wikipedia, but we already have the foundational model trained, how much of the new information from the tuning process gets injected into the model? Do you know what I mean? Like,
yeah, you're saying is some of this capacity already taken?
Yeah, exactly.
So the answer is actually a little bit more nuanced. So when you start from any model, right? If it runs out of capacity, it simply starts overwriting.
Okay.
Right. So the reason we created the notion of the taxonomy is that is what you want your model to remember. Everything else it can forget. Or you are accepting that everything else is okay if it forgets. Right. So yes, as long as this taxonomy is a reasonable size, which in this case is pretty large, it should. Or let me put it this way: I don't think the reason for not good performance is the model size. Sorry, the data size.
Okay. Yeah. Cool. I'm probably going to follow up with more questions while they dig into it more, but I figured I would just take the opportunity today. So thank you.
Right. Okay. There are no other questions. It's been great to be here. Thank you so much for attending.
And please, on the random samples channel, feel free to put if there are specific topics that people would like us to cover. Please feel free to put some ideas there. we'll try to make this. What we're trying here is like to make sure that we keep it very close to the product. But obviously, like it'd be good to know what is more urgent and less urgent, and so on and so forth. Awesome.
Ciao, guys.
Ciao.